Good morning, boys and girls. Today we're going to look at continuity, and I'm going to give you a formal definition for continuity. So our objective today is to determine the continuity of a function at a point and on an open interval, and then I want us to be able to use and understand the intermediate value theorem. Now, from what you know from pre-calculus, you may already understand that this function that you see before you is not continuous. It's discontinuous at x equals 3, and the type of discontinuity is infinite discontinuity. And we call it infinite discontinuity because it's going towards infinity. It has an asymptote. This piecewise function is continuous on its domain. From -3 to 3, it's continuous. There are no holes, there are no breaks, there are no jumps. This function is not continuous. It has a hole, and we call this a removable discontinuity. This function is not continuous. We call this a jump discontinuity, and it has a jump discontinuity at x equals 1. This function is also not continuous. Again, we call this removable discontinuity. It has a removable discontinuous point at x equals 1. From the lab that you guys did yesterday, you should have noticed that there were 3 conditions that must be met in order to prove a function is continuous. In pre-calculus, you may have learned something like a function is continuous as long as you don't raise, if you can draw it without raising your pencil. That's a nice little antidote. However, that is not a calculus definition. And in this class, when I ask you to justify something, you have to use a calculus definition. So if I ask you to justify a function is continuous, you cannot say things like, well, it doesn't have any, it doesn't have a hole, it doesn't have jump discontinuity. You can't say any of those things. If I ask you to justify that a function is continuous, you have to use the formal definition. And what is the formal definition? First, you must say that f of c is defined. So if you're taking the limit as x approaches 3, then you have to determine that f of 3 is defined. Secondly, you have to prove that the limit exists at c. So you'd have to prove that the limit exists from the left side, the limit exists from the right side, and therefore because the limit from the left is equal to the limit from the right, therefore the function, the limit exists. So you have to show the limit from the left side, the limit from the right side, they're equal, and then say that the limit as x approaches c exists. And the last thing you must prove is that the limit as x approaches c of f of x is equal to f of c. You have to prove all 3 of these in order to get credit credit for justifying that a limit exists. You have to show your work and you have to use proper notation. Calculus is a stickler for those things. So here's some properties of a continuous function. If your function is continuous and you multiply by a scalar, it remains continuous. If you add 2 continuous functions, the addition, the sum is also continuous. If you multiply 2 continuous functions, the result, the product, is continuous as well. And if you divide 2 continuous functions, the quotient will be continuous, well, providing g does not equal to 0. The function in the denominator does not equal to 0. These functions are continuous on their domain. Polynomial functions, rational functions, radical functions, trig functions. On their domain is the key there, because if you have a rational function 1 over x, it is discontinuous at 0, but 0 is not in its domain. So they're continuous on their domain. Okay, let's do an example. And this is found in your notes. I'm going to just do a couple of examples from your notes, so in that first section. So they're asking you to determine, to use the definition to determine if the function is continuous. Well, the first thing we need to prove in order to prove that this is continuous is that f of 3 exists. Now, why f of 3? Because x squared minus 9 is a continuous function. X minus 3 is a continuous function. And we just learned that if we divide two continuous functions, we get a function that's continuous on its domain. So x squared minus 9 over x minus 3 is continuous everywhere except for x equals 3, because x equals 3 is not in its domain given by the piecewise function, but that's also given because x cannot equal to 3 or to give us 0 in the denominator. So what we're going to do then, since we know that this is continuous everywhere, since we know x squared minus 9 over x minus 3, we know this is continuous everywhere except x equals 3. We only need to determine if f of 3 exists. And what is f of 3? Well, according to this piecewise function, f of 3 is 8. So we proved that first condition, f of c is defined. We proved that first one. Now we have to prove the second one. We have to show that the limit exists. So we have to show that the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right. And we're going to use our skills that we learned a couple of days ago by factoring. So we're going to find the limit as x approaches 3 from the left of x plus 3 over x minus 3. I'm just factoring the numerator over x minus 3. Those two cancel. So the limit as x approaches 3 from the left, if I do a direct substitution, I get 6. The limit as x approaches 3 from the right would be, I've already factored it, so it would be x plus 3. Doing a direct substitution again, I get 6 again. So what does that tell me? That tells me the limit as x approaches 3 from the left of f of x is equal to, notice how much I'm writing the limit. Notice I'm also writing the limit as x approaches 3 from the left of f of x. That's important notation. Is equal to the limit as x approaches 3 from the right of f of x, which is equal to 6. Therefore, the limit exists. Okay? So we've met two of the conditions. The function is defined. The limit exists. So is it continuous? No. Why is it not continuous? So I would say not continuous, because you always have to answer the question that you're asked, because the limit as x approaches 3 of f of x does not equal to f of 3. So it's not continuous because the limit exists, the function exists at the point, but the limit is not equal to the point. Okay? And I know that seems like a lot of writing, but that is what you would write to justify if a limit is continuous. Okay, here's another example. This time, this one is broken into 3. So once again, what do we know? X cubed is a polynomial function, so we know x cubed is continuous on its domain. X is a linear function, it's continuous. We know that that's continuous for all real numbers, and so is 1 minus x. So the only place where it may be discontinuous would be on the endpoints. So we only have to check the endpoints. That's the only place where it may be discontinuous. So to check our endpoints, we would do, so first thing we have to establish, does f of -1 exist? So f of negative 1, because it says less than or equal to here, I would have to use this middle function. So f of negative 1 is equal to negative 1. Now I need to see if the limit exists. So I have to say, does the limit as x approaches negative 1 from the left of f of x, that's equal to, now when I come in from the left, I have to use this top function, so that will give me negative 3. Negative 1 cubed, which is negative 1. Then I have to see, does it exist from the right? So I would do the limit as x approaches 1 from the right of f of x. And now I would use this part of the graph because that's where it comes in from the right. So that's going to equal to just negative 1. So yes, the limit as x approaches 1 from the left is equal to the limit as x approaches negative 1 from the right. It should be negative 1 of f of x is equal to negative 1. Therefore, the limit exists. So those three triangles, those 3 dots in a triangle means therefore the limit exists. The limit as x approaches negative 1 of f of x is equal to negative 1. So is it continuous at negative 1? Yes, it is continuous at negative 1. I'm sorry, my handwriting is so bad. When I write on this as a tablet, I don't think it likes left-handed people. So it's continuous because the limit as x approaches negative 1 of f of x is equal to f of negative 1, which is equal to negative 1. And so therefore it is continuous. So our next part of this would be to check to see if it is continuous at 1. So I want you to pause the video and I want you to tell me whether or not it's continuous at 1, writing your statements, and then we'll come back and see the correct answer. Okay, welcome back. So what you should have found is that the function is not continuous at 1. Notice what I did was I found f of 1 was 0. Then I found the limit from the left and the limit from the right and decided that the limit did not exist because the limit from the left did not equal to the limit from the right. Once I found that the limit did not exist, I did not have to go any further. I could stop right there because if it fails one part of the 3 definitions, it only has to fail one part in order to be discontinuous. So I could stop there and say the function is not continuous because the limit does not exist. I would like for you to finish the next 4 problems in that section and then come back and I will show you the answers. Okay, boys and girls, here are the answers to the 3 problems on the top of page 12. So just take a moment, pause the video, and check your answers. You can see that I don't think any of them were continuous, but please note my notation. Notice how we have to find the limit from the left and the limit from the right, and then if they did not equal, to state that they didn't equal. And also to state whether or not, once it failed one of the conditions, we can stop and say that the function was not continuous at those points. If you need to pause the video and write these down, feel free. And the last one I'll show you on the next page. And that is the answer for the last one. I tried to write down as much work as possible, but this is what you want this is how I want you to show your work. Again, if you need to pause the video to write this down, please feel free to do so. All right, on this problem, we're trying to find the value of a that's going to make the function continuous. So remember, the function ax squared, no matter what a is, will be continuous on its domain because it's a polynomial. And so so will 2x plus a will be continuous on its domain because it's a linear function. So the only place where it could possibly be discontinuous as a piecewise function is at the breaking point, which would be x equals 2. So we're going to have to make sure that ax squared is equal to 2x plus a when x is equal to 2. So we're going to start by writing the limit as x approaches 2 from the left of f of x must equal to the limit as x approaches 2 from the right of f of x. Okay, and so we're going to just substitute in the value of 2 into x. So that would give us a times 2 squared. So that would give us a times 2 squared is equal to 2 times 2 plus a, because I am substituting in 2 for each place I see x. So we have 4a is equal to 4 plus a. I would solve this equation for a. I'm going to subtract a from both sides. So I get 3a is equal to 4. So a has to equal to 4/3. That answers that first question. But now I need to justify that this answer is correct. So now I have to go back to the three points for the definition of continuity. So I have to prove that my new function would be f of x is equal to 4/3 x squared, where x is less than or equal to 2, and 2x plus 4/3 when x is greater than 2. So in order to prove this, I would have to show that f of 2, and f of 2 would be defined here. So I would have to say that 4/3 times 2 squared is equal to 16/3. Then I would have to prove that the limit as x approaches 2 of f of x, 2 from the left, is equal to the limit as x approaches 2 from the right of f of x. So that would be, again, 4/3 times 4, which we've already proved is 16/3. We'd have to see if that is equal to 2 times 2 plus 4/3. So we know this is 16/3. This is 4 plus 4/3. 4 to make it a third would be 12/3. So this would be 12/3 plus 4/3. So we get 16/3 is equal to 16/3. So therefore, the limit as x approaches 2 of f of x exists, and its value is 16/3. So is this function continuous? Yes. I ran out of space, so I'll do it up here. It's continuous because f of 2 is equal to 16/3. The limit as x approaches 2 of f of x is equal to 16/3. And the limit as x approaches 2 of f of x is equal to f of 2. So yes, it is continuous because all three conditions are met. Ta-da! Let's do another problem. Okay, so once again, so how about this? Why don't we pause this video and you try it on your own? How about that? Okay, so welcome back. The first thing, so again, x plus 1 is continuous on this domain. Ax plus b, continuous on this domain, and 3x is continuous. They're all linear functions, so they're continuous for all real numbers. The only place where they could be discontinuous would be at the endpoints, 1 and 2. So what we have to do is we have to find the limit as x approaches 1 from the left. So we have the limit as x approaches 1 from the left of f of x, and that would equal to, using this equation, that would be 1 plus 1, that would equal 2. Then we would do the limit as x approaches 1 from the right. So we would use this equation, and that would give me a times 1 plus b. Now, in order for this to be continuous, the limit as x approaches 1 from the left would have to equal to the limit as x approaches 1 from the right. So in other words, 2 has to equal to a plus b. Now we have two unknowns and one equation, so we need another equation. So let's do this. Let's say, let's find the limit at 2. So we're going to, let's get my cursor back. We're going to do the limit as x approaches 2 from the left. And we see that that is, as x approaches 2 from the left, that's going to be 2a plus b. Then we're going to take the limit as x approaches 2 from the right. And that's going to be 3 times 2, that's 6. So now we have another equation. We have 2a plus b equals 6. I have two equations, two unknowns. I'm going to have to go back to my Algebra 1 skills. So I'm going to use the systems of equation. So if I have 2 equals a plus b, and 6 is equal to 2a plus b, 2a plus b, I'm going to multiply the top by negative, and then I'm going to add those together. So I get negative 2 equals negative a minus b. So the b's now zero out, and I get 4 is equal to a. So if 4 is equal to a, so 2 is equal to 4 plus b, then b is equal to negative 2. So I found a and b. So that is the first part of that expression. Now I have to prove it. And yes, in order to prove it, I'm going to have to write 6 statements. I'm going to have to prove that the limit on the left is equal to the limit on the right at 1. And then I'm going to do the same thing at 2. And I've run out of space. I don't have any room to do that. So I'm just going to kind of write it in condensed form. So my proof would look like this. So at x equals 1, I would say that the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the right of f of x. And to find that limit, I would just do a direct substitution. I'd get 2 is equal to, a is 4, so that would be 4 times 1, and b is negative 2, so that'll be 4 minus 2, which is 2. So the limit as x approaches 1, oh, I don't know why I wrote it down there, of f of x is 2. So that would be the first proof. And then I would find that f of 1 is equal to 2. I'd have to list that as well. And then I'd have to say, because the limit, okay, that's really, I know my handwriting is bad, but that one just took the cake. I just can't take it anymore. We're going to change that because that I just couldn't even read that. That is the limit as x approaches 1. There we go. That's more legible. All right, and then we know that f of 1 is 2, and since the limit as x approaches 1 of f of x is equal to f of 1 is equal to 2, therefore f of x is continuous at x equals 1. And then we'd have to do the same thing for 2. So you have to prove that exact same thing for 2. I ran out of space, so we're not going to do it at 2, but that's how you would do that. All right, let's try another example. So this one is similar to the one that we just did. So I would like to for you to take a moment, pause the video, and complete it, and then we'll come back and look at it. Okay, so I've done the answers for this. We found that C was equal to 2 and D is equal to 0. We had to do systems of equation for that. And this time I proved both at x equals 1 and x equals 2. So if you were doing this on the test, you would have to prove both of these in order to get full credit. So I started by proving that the limits on the left is equal to the limit on the right. Therefore, the limit exists. And then I showed that f of 1 was equal to f of 2. And I concluded by saying, since the limit as x approaches 1 of f of x is equal to f of 1, which is equal to 2, therefore f of x is continuous at x equals 2. So again, in order to get credit for this, you'd have to show every single step. And then the last one, to prove it at 2, again, I showed that the left-hand limit was equal to the right-hand limit, so therefore the limit existed. I showed that f of 2 is equal to 8. And then the limit as x approaches 2 is equal to f of 2, which is equal to 8. And therefore, f of x is continuous at x equals 8. I really need you to show all of that work in order to get credit. Okay, if you would pause the video, and I want you to finish the problems on page 12 and at the top of page 14, that would be great. 12 and 13, I think. There's 3 problems left. If you could finish those 3 problems, that would be great. Okay, for this slide, I just gave you the answers without justifying them, but remember on a test, you would have to justify them. Okay, if you have any questions, let me know tomorrow in our synchronous learning. There's one last thing we need to learn today, and that's the intermediate value theorem. In calculus, there are a few theorems that you must know, and the intermediate value theorem, often abbreviated IVT, is one of those theorems that you must know. When using a theorem in calculus, before you can use the theorem, you have to make sure you state that the conditions for the theorem exist. And the only condition, well, there are 2 conditions that must be met in order for the intermediate value theorem to work. And the first one is that the function has to be continuous. So in order to use this function, you have to state that f is continuous. And you also must state that it's on a closed interval. Those are the 2 requirements for this theorem. So you have to state, in order to use it, you have to say that since the function is continuous and on a closed theorem, therefore the intermediate value theorem applies. An intermediate value theorem is a common sense theorem. What it basically says, if you have a function that is continuous, so if you have any function that's continuous, right, on a closed interval, and if you take 2 points on this function, I'm going to take just any 2 points. Let's say A and B. So this is point A, and this is point B. If the value of A is 5 and the value of B is 10, the intermediate value theorem says that somewhere, if this is somewhere on this interval, all of the numbers between 5 and 10 must be represented. All numbers between 5 and 10 must be represented. Somewhere on there. Somewhere on this interval, there must be all the numbers between 5 and 10 will be represented at one point or another. It could be represented twice, but at some point, all the numbers between 5 and 10 will be represented, which makes perfect sense because if it's continuous, that has to be the case. So the intermediate value theorem is used often to prove that there is a zero somewhere on the function. Because if I have a function, I'm just going to draw an ordered pair, a coordinate plane here, and it looks like this. Let's say it's a cubic function. It looks like this. If at this point is, let's say, -3, -4, and this point is 3, 4, I can't go from negative to positive without going through 0. So basically, if I were trying to prove that there was a 0 between -3 and 3 on this function, I could say, well, it went from -4 to 4, so it had to go through 0 because 0 is between -4 and 4. So that's basically what this theorem says, is that if you have a closed interval represented by the points f of A and f of B, then there has to be at least one number C in AB, such that C is between f of A and f of B. That's what it means. So let me give you an example of how you would use that. And again, the example I'm going to give you is going to seem very simple, but the IVT is often used when given a table of information. So how would we use this IVT? So we want to explain that it has at least one 0 on the interval 1, 2. Okay? So we're trying to prove that it has at least one interval, 1 0 between 1 and 2. Okay, so if I were going to use the IVT, the first thing I would say is that f of x is continuous. How do I know f of x is continuous? Well, we've said before that cubic functions, polynomial functions, are all continuous on their domain. So f of x is continuous. And on a closed interval. So I have to state that before I do anything else. And then I would find f of 1. So f of 1 is 2 times 1 cubed minus 3. So 2 times 1 cubed, that's 2 minus 3, that's -1. F of 2 is equal to 2 times 2 cubed minus 3. So that's 8, 16 minus 3 is 13. Therefore, f of x, there's got to be a value of f of x. F of x must equal 0 at some point. I could also say f of x has to equal to 12 at some point because because 12 is between -1 and 13. I can also say that f of x has to equal to 10 somewhere between 1 and 2 as well. I don't know what that value is. I just know that somewhere between 1 and 2, f of x has to equal to 0, which is what it asked. Not q. has to equal to 0. I could also say it has to equal to 12.3578 because that's between -1 and 3. It's somewhere in there it's got to equal to 2.64. Somewhere in there it's got to equal to pi because that's all of those numbers are between -1 and 13. So all of those numbers must be represented somewhere between 1 and 2 on this interval. Okie dokie, boys and girls, does that make sense? And that's the intermediate value theorem. And again, you're going to use that theorem often in calculus. And remember, in order to use the theorem, we got to prove that the theorem, we have to prove the conditions of the theorem, which in this case that it's continuous and on a closed interval. Okay, boys and girls, let's recap what we've learned so far. Today we learned that a function is continuous if f of c is defined, the limit exists, and the limit is equal to f of c. And we must prove all three of those in order to prove that it's continuous. And then we learned the intermediate value theorem. And it only works if a function is continuous and on a closed interval. And it says that if it is continuous and on a closed interval, there has got to be a point k such that k is between f of a and f of b on the closed interval. Okay, boys and girls, do your homework, do your summer assignment, and we will see you tomorrow.